Okay. Time to dive into these examples. We are going to evaluate these definite integrals. We're going to find the area between those functions and the x-axis from where it tells us to begin and end. We're going to find that area exactly, no more approximations. We're going to take advantage of our limit as n goes to infinity to get infinitely many rectangles. We're going to get this area perfectly. This is really exciting. Okay, starting off, this might sound familiar to you. We actually did a Riemann sum approximation for exactly this, x squared plus 1 from 0 to 6. I think we did R4. So now we'll get it exactly. And then we've got something brand new here for the second one. Okay, let's try it out. Evaluate the definite integral. Part A, integral from 0 to 6. Okay, 0 to 6, x squared plus 1 dx. Let's bring back what formula we're going to be using. We're going to be using the limit as n approaches infinity, summation from I equals 1 to n, f of x sub I delta x. Okay, let's look at each piece, going back using the theorem. So let's start with delta x. Delta x here, remember it's b minus a over n. So I can see a and b, 6 minus 0, and we're just going to put it over n since we're thinking n is going to go to infinity later. So here delta x equals 6 over n. The theorem also talked about x sub I. X sub I is a, well here a is 0, plus I times delta x. Well, we got delta x is 6 over n. So I'm going to think of this as 6 over n times I. I like to write the I next to it on this side. That's going to be helpful for the way the algebra plays out in just a moment. Okay, so these two things are making use of our theorem. Now we're going to plug these in to our formula. You know what? Let's start just with the x, f of x sub I. There's x sub I. I'm going to put that in, make our life a little bit simpler. Let's do this ahead of time. What does this even mean? F of 6 over n I. Our function, like what is f of x? Our function is the x squared plus 1. So plugging this in would be 6 over ni squared plus 1. And if we simplify that, 36 over n squared, I squared plus 1. Okay, perfect. So we're going to put this whole thing in for f of xi, delta x we know. Okay, here we go. Let's see, we got the limit as n approaches infinity. Summation from I equals 1 to n. 36 over n squared, I squared plus 1. And that gets multiplied by 6 over n. So far, so good. We're going to clean this up. We're going to kind of think about how the summation will work here. We're going to take advantage of, remember the formulas, the sigma formulas. Here we'll have an I squared, right? So we can kind of see maybe the formula for I squared is going to come into this. And then our very last step is to perform the limit as n goes to infinity. Okay, how are we going to go about this? We're going to do it carefully. First thing we're going to do is distribute this 6 over n. So limit as n approaches infinity, summation I equals 1 to n. Distributing the 6 over n would give us 216 over n cubed I squared plus 6 over n, like so. Okay. Now, what to do from here? Notice we've got 2 terms being added. Well, if you're taking a summation of 2 terms being added, you can take the summation of each one separately, right? A summation is simply adding a bunch of terms. So if these are being added, you know, we could do all these, add all of these first, then add all, right? The order wouldn't matter. So I'm going to perform the summation on each of these parts individually, like so. Now, take a look at this first one. This right here, 216 over n cubed, does not involve I, right? Our summation is for values of I equals 1 to n. We'd be plugging numbers in here. So this is like a constant relative to our summation, which uses I. So I can take this and put it outside, kind of like, you know, what we would do with the derivative. It'll work here. 216 over n cubed, that gets multiplied by our summation of I squared. Okay. Now, technically, we could do the same thing here with 6 over n, but I'm not. I'm going to leave that because I'm actually going to think of that one as being a constant, the summation of a constant. Okay. So far, so good. We're really doing a summation algebra here. Take a look. We've got the summation of I squared. We know the formula for this. Here, we've got the summation of a constant because it does not involve I. You remember those formulas. Let's see how this works. The limit as n approaches infinity. 216 over n cubed. This formula here for I squared, it was n times n plus 1 times 2n plus 1 all over 6. That whole thing gets replaced with this. Plus this one, this is a constant. The formula for a constant was take the constant and multiply it by n. So this is 6 over n times n. And that's going to work out nicely. Okay, this is great. We don't have those sigmas anymore. We've just got all of this expression involving n. We're going to clean all of this up. And then in the end, take the limit as n approaches infinity. And we'll have it. Okay, let's see. Some things are going to cancel out. We get one of our n's to reduce here right away. So that's n squared. The 6 reduces. That'll go back to being 36. And that'll become a 1. Obviously, n's cancel over here. Okay, so we got, I'll leave it like this for now. 36n plus 1 times 2n plus 1 over n squared plus 6. Starting to clean up well. We want to multiply all of this out. I'm just going to go ahead and write what all this becomes. You know, that could be like work on the side or something. It works out as 72n squared plus 108n plus 36. And that's that's over n squared and plus 6 on the side. Okay, looking good. We're still not quite ready to do this limit. Here's what we can do. Check this out. We've got a rational function with powers of n. Right? One way that we learned how to do this before was divide everything by the highest power of n when we've got a limit as n goes to infinity. We could divide everything by n squared. Even better, because there's only the one term here in the denominator, we could actually divide each of these terms separately by n squared and it'd have the same effect. So dividing each one by n squared, we've got 72 plus 108 over n plus 36 over n squared. And then plus 6 over here. Let's just add that on to the 72, make it 78. So here we go. Wow, we really cleaned that up well. What happens as n goes to infinity? Well, the 78 will just stay 78. These both get divided by infinity. They go to 0. And our answer for this definite integral is 78. It turns out the area between that function, x squared plus 1, and the x-axis from 0 to 6 is exactly 78 square units. What would that look like over, see if we can graph it. Y equals x squared plus 1 from x equals 0 to x equals 6. There it is, that big curved region. It's almost triangular, you know, but then it's definitely got that little notch at the bottom. That area, wow, that is exactly 78 square units. Not everything's going to come out to a whole number, obviously, but this one did. That is really amazing. Wow. Okay. So what did we do? Just kind of recap how we went through this. So first thing, start by finding your delta x and your f of xi using that theorem. So find xi, plug it in, clean it up as best you can. Then plug both of those in here to our formula with the limit and the sigma. Once you do that, distribute the delta x. Then you can start moving stuff around. Once you get comfortable, you can probably just jump, just jump over this middle step where we put it to each one. Just go ahead and take that, any constants out like that. Then take advantage of using our sigma formulas. And it's a lot of steps. It's a lot of writing, but most of them, they're going to have a very similar feel. So there our formulas go in, and then it's just working to clean it up, multiply it out. And eventually here we could divide everything and boom, that limit, no problem. We got our answer. Okay, we got another one, part B. It'll be good to do a second round of this now that we're a little bit more advanced. We understand how it works. The definite integral of 2x minus 4 from -1 to 3 dx. Okay, I'm going to copy over that formula again. The limit as n approaches infinity, sigma from I equals 1 to n, f of x sub I delta x. We got to start with delta x. Delta x equals b minus a, so 3 minus -1 over n. Here that is 4 over n. And x sub I, it's a this time we have a number, -1, plus I times our delta x. I'm going to write this a little bit neater as 4 over ni minus 1. Okay, now this we're going to plug into the function. There's our function right there. So f of 4 over ni minus 1, 2 times 4 over ni minus 1 minus 4. What's that going to be? 8 over ni minus 2 minus 4 is minus 6. So far, so good. Okay. Now this will go in for the f. We know delta x. Well, if I can keep all this on the same screen, the limit as n approaches infinity, sigma from I equals 1 to n, 8 over ni minus 6 times 4 over n. Okay. There we go. What do we do from here? Distribute. So that's 32 over n squared I minus 24 over n. Okay, then we're going to distribute the sigma. We're going to pull out this constant. So it's the limit as n approaches infinity, parentheses, 32 over n squared, sigma I equals 1 to n I minus, and I'm just going to apply it here since that'll be a constant, 24 over n. Looks good. Okay, time to apply our formulas. Formula on this, formula on this. 32 over n squared. This formula for I was n times n plus 1 over 2. Minus, and the constant, simply take it and multiply it by n. Okay, from here, we start to simplify, clean things up, right? N's cancel there, an n cancels there, 32 reduces, and we get 16 times n plus 1 over n minus 24. Not too bad. So this is going to be 16n plus 16 over n minus 24. Okay. Here again, we just have the n in the denominator. Let's just divide them each separately. (16 plus 16 over n minus 24). Well, the 16 would stay plus 0 minus 24. 16 minus 24, -8 in this case. We got it. Got it. Very nice. Again, like very similar steps, right? Different formula, you know, different details, you know, but same strategy. We got it. Hey, wait a second. I'm looking at that final answer, -8. I thought this was an area. Are you thinking that? This is the area between the function and the x-axis. How do we get a negative answer for the area? Let's take a look at the graph. This was y equals 2x. Y equals 2x minus 4. It's not on my paper anymore. Yeah, 2x minus 4. From x equals -1 to x equals 3. Okay, there it is. What's happening here? Well, you notice the function is below the x-axis for a while. It doesn't hit the x-axis until 2 and actually crosses over. So the area between the function and the x-axis, for a while, it's down here below the x-axis. And then we got a little bit of this area above the x-axis in that triangle. What's going on there? You know what, this black line, I'm going to change that. Let's make that gray. Okay, that's a little bit easier to distinguish between that and the x-axis. Okay, so we got this triangular area and this triangular area. What happens is when you find a definite integral, if there is area below the x-axis, that's considered negative area. Area above the x-axis is considered positive. So here, some of it canceled out. We had some little bit of negative area canceling with this little bit of positive area, but the majority of the area was negative, giving us a negative result. Let me sketch it out. Maybe a little bit easier to see this way anyway. So the line like comes up, you know, something like that. It passes through 2. So out here at 3, we could just say, we don't need all that. Here was 3. Back here was -1. So it's got more area beneath the x-axis than it does above. This area is considered negative area. And this bit above is positive area. So in the end, we had more negative than positive. So we got a negative result. You might think, do we really want that? I mean, if we're talking about area, shouldn't we consider it all to be positive and they would add together? No, we actually really want area below to be considered negative. The applications of definite integrals are way bigger than just finding areas of like curved spaces and stuff. And so we would want, you know, if our function dips into the negative y values, we want that to come back as a negative, you know, result, a negative area. You know, if you think about the example we did in the Riemann sums, the last example was with the race car. We approximated with the Riemann sum. Well, what if the car, you know, had a negative velocity? What if it was going backwards? That would affect the distance that it would have traveled in the end, the distance that we calculated. So we would want a negative velocity to be considered as going backwards on the track. If we're trying to find the total distance it travels, right? We wouldn't want to just be thinking, what's the distance that the car moved in any direction? No, we'd want to say like, when was it going forward? When was it going backwards? So we like that to come out that way. You know, you also notice, it's kind of interesting. These are just a couple of triangles, aren't they, in the end? I think we could have found that answer. In this case, we didn't even need to do all this calculus. We could have just found the areas of these triangles, right? And considered this area negative and this area positive and gotten that result. Let's see. I don't know the base and the height of them, but that wouldn't be too hard to figure out. But I think, yes, some of this triangle is going to cancel out like that much. And then the rest of it's going to be -8. Interesting. Now we like to do the calculus. We wanted to practice that, of course. But that kind of leads into something else. You know what? We better stop this video here. And then talk about where I was about to go in the next video.